So today in this video we are going to talk about um, equivalent conductivity and molar conductivity. Before I talk about these terms, let us rewind what the equations or the mathematical expressions that we learned in the previous video. If you recall, we learned the Ohm's law, which is R is equal to E by I. Then we talked about conductance, which is 1 upon R. Then we also related resistance to the length and area of the conductivity cell, and we related in this particular manner, and rho is your resistivity. And then we came finally to the expression where we related the conductance with the conductivity or specific conductivity in the using this particular expression. So these were some of the expression that we talked about, and these expressions are valid for all types of conductors. Okay. Now, when it comes to electrolytic conduction, uh, we, when we are dealing with electrolytes in particular, it is more appropriate to talk in terms of the concentration of the solutions. Okay, because when you compare two different electrolytic conductors, you would talk in terms of the concentration of the solution of different electrolytes. Okay, so therefore we require certain conductivities which could be related in terms of concentration. For example, in solutions we relate the concentration as normality, or we relate it to molarity. Okay, so we have in electrolytic conduction these terminologies. For example, when we are talking about normality, the conductivity that we talk about is the equivalent conductivity. In this, at the same time, when you are using molarity as a concentration term, the conductivity that you talk is the molar conductivity. So these are the two different conductivity terms that we use in electrolytic conduction. Okay, so let's first start understanding the equivalent conductivity. So let's try to define what do you mean by equivalent conductivity. So as you can see here, I have written the definition of equivalent conductivity. So equivalent conductivity, as I already told, here we are dealing with normality. So you know, in normality we talk in terms of gram equivalence, a number of gram equivalents present per liter of the solution. Okay, so whenever the concentration term that we use is in terms of gram equivalent, the conductivity that we talk is equivalent conductivity. So definition wise, equivalent conductivity can be defined as the conductance of a solution of volume V centimeter cube containing 1 gram equivalent of electrolyte, provided the distance between the electrodes is 1 centimeter and the area is such that the whole solution is contained between them. Now it's pretty simple to understand, because here we are talking in terms of conductance. If you remember in the previous video, I told you that conductance is something that is more appropriate when we talk about electrolytes. Okay, so therefore equivalent conductivities, when we are talking in terms of concentration, here means that it is the conductance of a solution of V centimeter cube containing 1 gram equivalent of the electrode. So that means if you have a solution, okay, and the concentration of the solution is 1 gram equivalent, and the volume of the solution is V, then the conductance that you get for this particular electrolytic solution would be the equivalent conductivity. Now here an important thing to note is the distance. For example, if you talk about the electrolytic solution, suppose this is the solution and you have V centimeter cube, okay, and the concentration here is 1 gram equivalent, okay. Now this solution, when you measure the conductance, this conductance is what you refer here as the equivalent conductivity, and that you represent using a symbol that is lambda EQ. Lambda EQ. So that is what is written here. It's represented by a symbol that is lambda EQ. Okay, and this is called as lambda. Okay, this can be referred to as the capital lambda, because you know lambda is also written in this particular fashion. So this way of writing the lambda, you can call it as a capital lambda. Okay, so the conductance of this solution would be the equivalent to the equivalent conductivity. Okay, so this is what equivalent conductivity means. Okay, now we need an expression for this equivalent conductivity. Only then we can use it for calculating the conductivity, equivalent conductivity of various solutions. Okay, it is important we have a mathematical expression. So here we need to relate this lambda EQ to the parameters which we actually can measure. Okay, so how to come to that particular expression? You don't have the derivations, but you should understand how you get the equation. Okay, so let's look carefully at the definition and therefore try to understand the expression. Okay, so suppose you have a solution whose now before talking in that terms, if you remember, we related conductivity with the conductance. Okay, in the previous video we talked about the definition of conductivity, and we related conductivity to conductance. Okay, so at that time I told you, if you have a conductivity cell having a length of 1 centimeter and an area of 1 centimeter square, okay, or in definition I told you, if it is a conductor having a volume of 1 centimeter cube, okay, in all these cases the conductivity would be equal to conductance. Okay, so that we learned in the previous video. Okay, now keeping that in mind, now if we consider a solution, a electrolytic solution having a concentration that is 1 gram equivalent in 1 centimeter cube of solution. Okay, so we are talking about a electrolytic solution having a concentration of 1 gram equivalent in 1 centimeter cube of solution, and supposing that the dimension of the electrolytic cell is equivalent to 1 centimeter cube. So that means L is 1 and A is 1 centimeter square. Okay, so that the area, the total volume become 1 centimeter cube. Okay, if that is the case, then the conductance that you measure for this particular solution, by definition we just now told you, if the concentration is 1 gram equivalent, then the conductance that you measure for this particular solution would be equal to the lambda EQ. Okay, so that means for this particular solution where the volume is 1 centimeter cube and the concentration is 1 gram equivalent, the conductance that you calculate is equal to the lambda EQ. Okay, that is equivalent conductivity. And I just now told you, if the dimensions of the cell is 1 centimeter cube, okay, in that case what happens, the conductance is equal to conductivity. So that means you can rewrite this expression in this format where lambda EQ is equal to specific conductivity or simply conductivity. Okay, now so this is an important thing that we got, because just now by definition we tried to relate the lambda EQ to conductance. Okay, and uh, here by argument we found that lambda EQ is equal to specific conductivity. Now if you consider a solution of 1 gram equivalent, okay, consider a solution of again of 1 gram equivalent. Now it is a V centimeter cube. Okay, that means some volume V centimeter cube of solution. In that case, if you want to calculate the lambda EQ, so we just now said that for 1 centimeter cube of solution, lambda EQ is equal to the specific conductivity. So that means for VCC, the lambda EQ will be simply K multiplied by V. So this is the first expression, an important expression that you should keep in mind. Okay, so this is an expression for calculating the lambda equivalent conductivity, where we have related the equivalent conductivity to specific conductivity times the volume. Now this volume is the volume that contains 1 gram equivalent of the electrolyte. Okay, so this is one type of equation that relates the lambda EQ to the volume. Okay, now suppose we are given normality, so that the concentration is now not now 1 gram of equivalent, but rather it is some n gram equivalent of solution in 1000 cc. Okay, suppose we are given the normality of the solution. Now how then it could be related? It's pretty simple, because normality means n gram equivalent in 1000 cc of solution. So that means the volume that contain 1 gram equivalent means it is simply 1000 divided by n. Okay, so that means 1 gram equivalent is contained in this volume of the solution. So that means this V here you can substitute with this particular value. Okay, so when you do that, what you get is another expression where lambda EQ is equal to K times 1000 upon n. Okay, so n is nothing but the number of gram equivalent which we obtain from the value of the normality. Okay, and these things you are pretty aware of, because you know uh, when you try to learn about solutions. Okay, now here if you talk about the units of lambda EQ, it's also again very simple, because K or the specific conductivity, the unit was per ohm per centimeter. Okay, and 1000, this is centimeter cube, divided by this n is in gram equivalent. Okay, so accordingly the centimeter inverse centimeter cube, when you add them together, it becomes per ohm centimeter square gram per equivalent. So this is the unit of the lambda EQ. And if you can write it in another format, because we know the per ohm can be written as Siemens, so it is Siemens square gram EQ per EQ per gram equivalent. In SI units, if you want to write it, is Siemens meter square gram EQ per equivalent. Okay, so this is the unit that you get for the uh, lambda EQ, that is your equivalent conductivity. Okay, so this is when you have concentration in terms of normality. Suppose you have concentration in terms of molarity. Okay, so that means when you are talking solely in terms of moles, okay, moles of the solution. Okay, in that case, the definition would be pretty similar. Molar conductivity can be defined as conductance of a solution of VCC containing, now here it was 1 gram equivalent, but now it is changed to 1 mole of electrolyte, provided the distance between the electrode is 1 centimeter and the whole of the solution is contained between the two electrodes. Okay, and we represent molar conductivity using this particular symbol, that is capital lambda with a subscript m. Now, with a similar argument that I just now talked about, in that using that argument itself, you can come to similar expressions. So, lambda m could be simply conductivity times the volume. Now, here this volume is the volume of the solution that contains 1 mole of the electrolyte. Using the similar arguments, if you are given molarity, you can use this particular expression to calculate the molar conductivity. Again, if you try to write the units, it's simply conductivity unit is per ohm per centimeter. This is 1000 centimeter cube divided by molarity. Therefore, we are talking in terms of mole. So, therefore, the units reduced to per ohm centimeter square per mole. Okay, now if you talk in terms of you can write this as Siemens also, and when it is converted to SI units, you just have to change the centimeter square to the meter square. So these two important uh, conductivity terms is very important when you talk about the what you say the electrolytes. So in electrolytes, equivalent conductivity as well as the molar conductivity is very important, and you should be knowing the expressions that we learned. If you just know the format of this expression, the lambda EQ and lambda M, they are pretty much similar expressions we use to calculate. So please keep in mind these expressions because they are essential, especially to solve the numericals related to these topics. Okay. So thank you for watching. We'll talk about the measurement of these molar conductivity as well as the equivalent conductivity. I will talk about how they are measured very briefly. Just I'll show you how it is done using conductivity cell, and then we will talk about some numericals related to these to the calculation of these particular molar conductivity and equivalent conductivity. So thank you. Have a nice day.